So I will start with the main result. It says that the sample complexity of empirical risk minimization for strict saddle objective is roughly the same as in the strongly convex case. Our proof technique involves extending stability analysis to a non-convex setting, and we discuss applications to PCA and ICA. The problem setup is as follows. We would like to approximately minimize the expected risk over subset W of RD, where the expectation is overdrawing parameter Z according to the distribution D. The input to the learning algorithm is, as usual, a sample of n points drawn IID according to the distribution D. And we focus on ERM, and we denote by W hat the minimizer of the empirical risk. The sample complexity, which is a function of epsilon, is defined to be the minimal size of a sample S for which the expected risk of W hat is epsilon close to the optimal risk. As we know, many important learning tasks are non-convex, and this brings several challenges such as spurious local minima and saddle points. And a promising direction is extract appealing properties of nice non-convex functions. One such family is a family of strict saddle functions. So informally, strict saddle points are saddle points which can be relatively easily distinguished from local minima, mostly using second-order information. And here's the precise definition. We say that the empirical risk is alpha gamma tau strict saddle if for every point W at least one of the following condition holds. So the first possibility is that W has non-vanishing gradient. This means that we are relatively far from a stationary point. The second possibility is that we are near strict saddle, and this is quantified by the Hessian. We require the minimal eigenvalue of the Hessian to be strictly negative. And the last option is that we are located in a strongly convex region around the minimum. Another assumption which we make is that all local minima are global. This assumption is indeed satisfied by all known strict saddle objective as far as I know, but we make this as an optional assumption, that is we will be able to interpret our result also in the absence of this assumption. And we also assume that Lifshitzness and two-sided smoothness of the objective. So examples of functions that satisfy these assumptions include tensor decomposition, ICA, matrix completion, and principal component analysis. And as we know, recent research has yielded efficient algorithms that use either second-order information or only first-order information in order to minimize such functions. So the precise main result is that suppose that the empirical risk is strict saddle with high probability, then the sample complexity is bounded above by the maximum between these three terms. So the first two terms are independent of epsilon. They depend on the ratio between Lifshitzness and smoothness and strict saddle parameters. And the last term is actually identical to the strongly convex case, and it reveals linear dependence on 1 over epsilon, so we get fast rate in this case. So we conclude that statistically, at most cases, strict saddle problems are not harder than strongly convex problems. Okay, so as I said, we can remove the assumption that there are no spurious local minima. And then instead of discussing empirical risk minimization, we discuss algorithms that converge to the local, to some local minimum of the empirical risk. And the same hyperbound that we established show that we get epsilon approximation of some true local minimum. So as an example, we consider PCA, where we would like to recover the leading eigenvalue of the covariance matrix. The sample complexity under boundedness assumption is 1 over epsilon square, and this is known to be tight. However, if we assume that there is a gap of order G between the first and the second eigenvalues, this assumption actually translates into strict saddle property of the objective with parameters proportional to the gap, and we get sample complexity bound of 1 over G squared plus 1 over epsilon G, which is better when epsilon is smaller than G. Okay, so I want to give the proof sketch. So we use algorithmic stability, and algorithm is algorithmically stable if slight change in the input of the algorithm doesn't change its output much. And stability is related to learnability in a very strong sense. It is necessary condition for learnability, and it is sufficient for generalization. We define stability by introducing n leave one out minimizers. W at I corresponds to removing example I from the sample. And delta I quantifies the loss incurred to W at I by not observing this example. And the average stability complexity, which is again a function of epsilon, is the minimal size of a sample for which the expected average of the delta i's is at most epsilon. And it is a well-known fact that the sample complexity is dominated by the average stability complexity, and therefore it is sufficient to bound the stability. And now the key idea would be to reduce to the strongly convex case. So I remind you that the rate for strongly convex loss is at most 2 rho square over alpha epsilon. Rho is the Lifshitzness, alpha is strong convexity. So the key lemma is that for large enough n, which is independent of epsilon, all the leave one out minimizers lie in strongly convex regions around minimizers. And assuming the lemma, the proof of our main result proceeds as in the strongly convex case. So the proof of the lemma is very simple. It's sufficient to exclude the possibility that any leave one out minimizer as large gradient. And the second possibility that it is located near a saddle point. So if we define by L at minus I to be the empirical loss when we exclude example I, then by using first order condition with respect to W at I and by using Lifshitzness, we know that by adding this example back, the gradient cannot increase too much. So we exclude the possibility of large gradient. And similarly, by using second order conditions and smoothness, we get the desired bound on the Hessian, which implies that we are not near a saddle point. So this is the idea behind the proof in the unconstrained setting. However, all the applications that we discussed are actually constrained. So we consider the case of equality constraints, and while the proof here is a little bit more technically involved, the key idea is to reduce the unconstrained setting using KKT conditions. So to conclude, we show that statistically strict saddle problems are almost as easy as strongly convex problems. Thank you. If we, okay, you talk about the result on SGD that?
Probably not SGD, just the exact gradient descent.
Okay.
Would there be, like, if I don't change the assumption in the talk, can you show that, like just to change one data point in the data set, can you show that running gradient descent on these two very similar data sets actually converge to a similar settlement?
So as long as a gradient descent is empirical risk minimizer, which is the case in this, under these assumptions. So this is true also for gradient descent, right?
But there could be multiple global means.
Okay. So this is why we assume that all local minima are global, and so in some sense, without loss of generality, we can assume that they are located in the same region. Okay.
Okay, thanks, Alon again.